Hi, and welcome to another Hopper on microcontrollers video. Hopper is a modern semicolon and curly brace language designed to run on microcontrollers, a little bit like Java or C#, but obviously constrained so that it runs on small devices. It runs on a 6502, so it's quite lightweight. Anyway, this video is about the RP2350 from the Raspberry Pi Foundation, and specifically about their choice to put, to make this unique design where they have four cores on the four CPU cores on the same microcontroller. So they've upgraded from the Cortex M0 cores to two Cortex M33 cores. And in addition to that, they've got two Hazard 3 RISC-V cores. Now, you can't use them all at once, but you can boot the chip into either ARM mode or RISC-V mode. So why'd they do this, and why do we care? Well, ARM is a licensed technology, which means it's not open source, and they're required to pay a licensing fee to use it. Whereas RISC-V is not. It's completely open source, so no license fee. Which means in the long term, I could see them trending, if there's no resistance, trending to just ditching ARM and running on RISC-V. So makes me kind of want to make Hopper work on RISC-V for that reason, right? So what did it take to build for RISC-V? So the Hopper runtime is built using the Arduino IDE and using the board manager from Earl Filhauer. So if we go and have a look at board managers, so the way you get a board manager into the Arduino IDE is by including a URL. So Earl Filhauer's Arduino board manager, or RP2040 and RP2350 library support. So I already did a video about supporting the Raspberry Pi Pico 2 boards, but this one is about supporting them with RISC-V architecture. So let's go switch back to the Pico 2 board, and then when you've got that board manager installed, you get a new menu item called architecture, and you can switch between ARM and RISC-V, and that's all you do. Switch to the one you want. And as usual, when you're building for building the runtime for Hopper, you need to select some flash drive size. The default is no flash, no flash storage. So we want flash storage as big as possible, and the sketch as small as possible, because our sketch fits easily into 1 megabyte. Everything else is the default except for fast rather than small for optimization. Makes the UF2 slightly bigger, but it does also make it slightly faster. And then you just compile it, and you end up with a new UF2 file. So that's how you would build it yourself. But as usual, I save you the effort, so you don't need to bother with that. For the most common cases, I make UF2 files. And I put them in. So there's a new release for RISC-V support, and for these boards, and I've added a few new UF2s. So I specifically do Challenger board UF2s because the Challenger has a different Wi-Fi chip to the Raspberry Pi Pico W, and the Pico 2, the Pico 2W hasn't been released yet. So the more recently added UF2 files were the one for the Pico 2 and the one for the Challenger board with the with Wi-Fi. There's another Wi-Fi board coming, the Pimeroni Pico 2W, and I've got one in the mail, so there'll be another UF2 for that one when it arrives. And then today's new UF2s are the RISC-V ones. So it's Pico 2 RISC-V, which works with almost all RP2350 boards. I've tested it with Pimeroni's boards. I've tested it with I tested with a couple of different boards. but we need, again, we need a separate one for the Challenger because of its Wi-Fi chip. When building these, it's interesting to note that the RISC-V one is slightly bigger. So it went from 466K to 520K. And in the case of the Pico 2, it went from 495 to 612. So, yeah, from 494 to 520 and from 495 to 612. So, just, curiosity, the RISC-V object code is slightly bigger than the ARM object code. And then you just drag and drop these onto your, you hold down the boot select button and drag and drop them onto your microcontroller the same way you would have done before. So yeah, that was the only change with this update, was these two. Let's go and have a look at the... so what did I do? I added another bit. So if you're using if you want to know whether you've flashed it is your board currently running as ARM or as RISC-V, because it can be one or the other. So to hop a monitor, I added a new bit to check. So it says here where it says it's a microcontroller running. So normally this would say MCU or 6502 or Z80. So in addition to MCU, I'm now saying it's MCU with the RISC-V architecture. So if it doesn't say RISC-V here, it means that it means it's running as ARM. Okay, and I tested with my usual benchmarks. So Mandelbrot. So this is running RISC-V right now. So this runs in like 845 milliseconds. Knowles RetroLab, which basically just tests addition and loops. It's a fundamental benchmark, originally written to test BASIC. 174 milliseconds, and then the other one was the Sieve benchmark from the prime number benchmark from Byte magazine from like 1980. And yeah, so I tested a bit. I've tested a few other things as well, but my main curiosity here was how do these perform? I was just curious, like, is there a big performance difference between the ARM cores running at the same clock speed and the RISC-IV cores? And it's sort of mixed. So in my experience, the Mandelbrot runs like slightly slower, like 17% slower. Knowles RetroLab, which is like tight loops. I can show you what they look like. So Knowles RetroLab runs 2 for loops nested, and it adds numbers together to an expected outcome. And I only use long for the accumulator because long is a reference type in Hopper, so it would make this benchmark a bit unfair if I didn't do that. Anyway, so that's Knowles RetroLab's benchmark, prime number benchmark, loops and arrays, and if statements and whiles and stuff. And then the Mandelbrot is just a pretty picture and it's Gordon Henderson's text-based Mandelbrot, and it's just integer arithmetic basically, and it does more I/O during the benchmark. So it's the only benchmark that does I/O during the actual timing, as opposed to just printing the results. Anyway, the Civ benchmark, the prime numbers runs about 12% faster. Knowles RetroLab loop test runs 25% faster, and Mandelbrot runs about 17% slower. So they pretty much there's not a massive difference. It's not like the one's 5 times as fast as the other. And I reckon we're using GCC here for building the runtime. The Arduino IDE is using GCC, and you probably find that the ARM compiler has had a lot more time to be optimized, whereas the RISC-V one is still relatively new. It's not that new, but if we look in another year or so, are they going to be on par? Probably. There's going to be all faster. So RISC-V should be faster because it's a much newer architecture. The ARM architecture dates back to the 80s. And RISC-V, they've had a lot of, there's been a lot of computer science since the 1980s to learn from, and I expect the RISC-V chips to ultimately be faster. Anyway, that's the short summary of what we can expect. So it means Hopper can now run on RISC-V on these RP2350 boards. If you do some benchmarking and discover things that are interesting, please add to the comments and let us know. If you have more questions on this, also add them to the comments. There's my quick overview of RISC-V on the RP2350 boards, 2350 boards. Thank you.